Okay, so in this video, we're going to be looking at homogeneous solutions and null spaces. Actually, these are basically the same thing, but we often encounter them in slightly different places inside our linear algebra course, and we kind of forget that they're actually related to each other. So there are a number of applications in linear algebra that depend on the solution to a system of equations that are homogeneous. For a system to be homogeneous, we need to be able to write all the equations of the system in the form of having all the variables on one side and the only constant in the equation to be 0. In a matrix form, this would be written as AX is equal to 0. Systems of this sort always have a solution. For instance, we could let all the variables be equal to 0. That is called the trivial solution, since every system has it. However, what we're looking for is a solution that is less boring. We are looking for the possibility of a solution that has not all the variables equal to 0, but still manages to solve the system. So these interesting solutions of the homogeneous solution, these non-trivial solutions, we first are going to begin by discussing how to solve dependent systems with finite numbers of solutions and how to express our solutions in vector form. So dependent systems of equations tend to arise when there's not enough information to solve for every variable exactly. So we could have, for instance, a system where we have only two equations and 3 variables. We could also have a system where we had 3 variables and 3 equations, but the third equation wasn't contributing any new information to the system. And so it was as if there was not a third equation. In a situation like this, we're going to have at least one variable we can choose freely. In other words, we can make it be anything. But then once we pick that solution, then the rest of the system will be determined. So we're going to need to be able to write the system in parametric form, since it's going to be dependent upon that choice of that one of those constituent components. Now, first, we're going to solve the system. We're going to write this in augmented matrix form, and then we're going to row reduce this. I did this in my calculator, and I got this system. And again, we want this in reduced row echelon form. We need to go all of the way. We need to get rid of, anytime we have a pivot, we need to get rid of entries above it. Otherwise, the math will be messier. But in this case, I've gone all the way, and this is the matrix that I get. And I'm going to write these equations back out again. So this means that x1 minus 7/8 x3 is equal to 11/4, and x2 plus 13/16 x3 is equal to -5/8. Now, since there is no third equation for x3, we're going to designate this as our free variable and just say x3 is itself. And then I'm going to move everything over to the other side of the equation, so I can have all my x3 coefficients lined up, and then any constants. Again, this is just a general dependent system, not a homogeneous one in this case. Now, in this case, what we're going to do is we're going to extract our coefficients for x3, put them in vector form, and then our constants can also go in vector form. And so this would be a suitable version of our system. We can also represent this x3 in terms of a parameter if we wanted, in order to try, for instance, to get rid of some of our crazy fractions. A common approach would be to let x3 equal, in this case, 16t. And then the 16 can be distributed through the vector here to eliminate all of our fractions. That is also in parametric form. That would also be fine. But this form of the solution allows us to find any other solution to the system we would simply choose x3 to be some value. And then when we add the resulting vectors together, we would get one possible non-trivial solution for the system. So here, if I let x3 equal to -2, then multiplying here, I get this vector. I just add the constants. Again, I'm not multiplying the whole thing by -2, just the first component where the x3 is. And if I add these together, then I end up with this as my solution. Again, it is a solution. Because x3 is free, there's an infinite number of solutions. Any value I choose for x3 is going to produce a slightly different solution. Now, as I mentioned, we can completely parameterize this. And at least in the vector that's multiplying the variable, we can eliminate the fractions. This is typical normalization for these kinds of problems. We would let 16t equal x3. The 16 can then be used to eliminate our fractions from our original vector. And the constant, of course, cannot be altered like this. Now, the idea here for the dependent solution is that a dependent solution where there are no constants will have to go through the origin because all the zeros is a possible solution to a homogeneous system. If we have a dependent system with constants, so that's not homogeneous, then in fact, the dependent system will be the original homogeneous solution, but shifted off by some constant vector. So there will be a constant that moves that vector solution from the origin to some point that does not go through the origin anymore. So these vectors are actually related to each other. If we had solved this system, we go back up here, if we had solved this system with 0, 0 over here instead of 7, 8, we would only have gotten this part of the solution because these constants came from the fact that that was not 0, those were 7, 8. These would otherwise be 0 if we had started with 0, and we would just have this component here. And so that's why we say that this p vector is that constant, that shift away from the origin. The parameter times the solution vector is the homogeneous solution. And then if you add the homogeneous solution to that constant shift, then you get the solution to the dependent but non-homogeneous system. Now, obviously, some of our dependent systems and therefore our homogeneous systems could have more than one free variable. But if we're thinking about it in terms of something that we can visualize, too many things can't be visualized very easily when we leave the three-dimensional realm. All right, now let's do another example. Now, this will be an actual homogeneous system, and we're going to see if we can find any non-trivial solutions and then write them in parametric form. So our constants are all 0 in the augment. You can write them out as 0, although it's very common in homogeneous problems to actually leave out the column of zeros because it's not going to change as you do row operations on it. So just remember that the augment is 0. But we create the augmented matrix initially the same way that we would for any other system of equations. But again, I'm going to leave out the zeros because they just make copying the matrix out more difficult. And nothing that I do to it is going to change these from being 0. Now, if, again, I used my technology to row reduce this matrix, again, depending on your particular situation, you may have to do it by hand, but it takes a while, but it can be done. And again, we want it in reduced row echelon form. So once we get our pivots, we need to make sure that everything above our pivots is also turned to 0. for a problem like this, that's just one extra step. And I get this matrix. I have 2 rows of zeros since I had a 4x4 matrix to start with. And I have 2 columns that don't have pivots in them. So I have 2 free variables in this case. Now I'm going to start basically the same way that I did before. I'm going to pull my equations out of my matrix. So x1 and 2x3 and minus 8x4 is 0. Remember, that's a 0 out there. X2 minus 3 halves x3 plus 13 halves x4 equals 0. And both x3 and x4 are free. And then we're going to move both x3 and x4 in our first 2 equations over to the other side. Now, sometimes it may help to line up the coefficients on the right side. But on the left side of our equation, we have x1, x2, x3, x4. That's just x. And then the first vector of our solution, of our parametric form, is going to have the coefficients of x3. So -2, 3 halves, 1, and then x4, it has no x3 in that expression, so that's a 0. And then the x4 coefficients, 8, -13/2 is 0, because there's no x4 on this line, and then 1. And then, again, if I want to clear my fractions, I can let x3 be 2t and x4 be 2s. I need to pick a different parameter because these are not tied together. They are still independent of each other. And so if I distribute the 2 through these components, I end up with -4320 times t and 15. That should actually be 16, -1302 multiplying s. Again, that should be 16 because 8 times 2 is definitely 16 and not 15. Typos. Now, because there are 2 free variables, this system is built on a linear combination of 2 different vectors, both of which can be scaled freely. And then the coefficient matrix in the original problem was 4x4, and the solution vectors have to match the dimension, the n dimension, the number of columns of the coefficient matrix. This is necessary because the solution has to satisfy the equation ax equals 0. Otherwise, the multiplication can't be defined. So the solution has to be n by 1. So in the first example, we had a 2x3 coefficient matrix, and all of our solutions were 3x1 vectors. Now, until this becomes automatic, it's a good idea to check that the dimensions of the solution with the coefficient matrix still work using dimensional analysis to make sure the multiplication is defined. It is very common for students, for instance, to forget to add in the free variables, for instance, at the bottom of the equation, and not get vectors that satisfy the required multiplication properties. So this is a way of helping ensure that you remember to make the vectors the appropriate length. Now, when we consider the null space of a linear transformation, that is just defined as the set of vectors that map onto the 0 vector in the codomain. The null space is also sometimes called the kernel of a linear transformation, because this is essentially the solution to the homogeneous system, because we're taking a matrix, multiplying it by a vector, and mapping it onto 0. That's our homogeneous solution. We basically will solve for the null space in the same way that we did in our previous examples. However, in these problems, we generally don't have an explicit system to start with, just the matrix. So another difference is that we will list the vectors in a set in the solution rather than keep it technically in parametric form as we were doing before, because we're listing a basis for the null space as opposed to a parametric form of the solution for the homogeneous system. But a lot of the procedures are going to remain the same, and it is conceptually rooted in the same idea. So here's our transformation matrix, our linear transformation. And just as we saw with once we turned our system into a matrix, we row reduce. And so that's what we're going to do. And again, I use technology to put this in reduced row echelon form. And I can see that I have a pivot here. Everything above it is 0. My next pivot is actually here. Everything above it is 0. So this is in reduced row echelon form. Again, don't stop at row echelon form. You have to go all the way and finish clearing out these zeros for everything above all of your pivots. Now, as we did in example 2, we're now going to write the reduced matrix as a system of equations and declare the free variables. So our first equation, x1 plus 2x3 plus x5 is equal to 0. Again, if we go back, x1, no x2, 2x3, no x4, x5 equal to 0 because it's a homogeneous solution. x2 plus x3, x2 plus x3, no x4 and x5. And then x4 and x5 in the bottom row here equals 0. Now, the columns that don't have pivots in them are x3 and x5. So those are our two free variables. Up here, we're going to move everything over to the other side of the equation. And then again, we want to collect our coefficients for our x3 and then collect our coefficients for our x5. So for x3, we have -2, -1, and 1. And then no x3s down here, so 0, 0. And then collect our coefficients for x5, -1, 0, 0, -1, 1. And again, I put these in the order x1, x2, x3, x4, x5, so that I have x on the other side of the equation, because the order matters. So the null space is then reported, again, the basis for the null space is then reported as a set of these two vectors. Any linear combination of these vectors will map onto the 0 vector if multiplied by the original A matrix. So again, you'll note that the original matrix was 3 by 5, and our solution vectors are 5 by 1. Now, solving for the homogeneous system or the null space is useful in a number of applications in linear algebra. We've seen them in other videos for equilibrium vectors in Markov chains or solving for eigenvectors. So for example, in the Markov chain case, we're solving this equation, PQ equals Q. We move the Q over to the other side. We end up with a matrix times Q is equal to 0. The Q vectors are the solutions to the homogeneous system for P minus I. Likewise, for eigenvalues, we have this relationship. A times this vector V is equal to lambda times the vector V. Again, collect everything on one side of the equation, factor out, there should be a V, factor out our vector, and then we're finding the null space for our A minus lambda I matrix.